Hello everyone, welcome to 369 Chemistry, and in this video we are going to talk about your stereoisomerism in coordination complex. Okay, so this is same as in your organic chemistry. We have stereoisomers like geometrical isomers, cis and trans isomers. These are called your geometrical isomers. Then we have enantiomers, okay, which are mirror images of each other but non-superimposable. So these things are also there in your coordination complex. So we will discuss all these things. See, in coordination complex, what happens is that, see, when stereoisomerism or stereochemistry means when you have a molecule and you are rotating it around an axis. You are imagining a molecule in a 3D plane, and you're rotating it about any axis like x, y, x axis, y axis, or z axis. Okay, so when you rotate, you get different spatial arrangements. So these spatial arrangements are only called your, you can say, geometrical isomers. Then these are two types of, that is your geometrical isomer, and you have another one, that is your optical isomers. So geometrical isomerism, okay, in your coordination isomerism cannot be exhibited by the coordination compounds having two or three coordination number, as it is possible only for your your octahedral and square planar complexes. These here, the geometrical isomers, they here the coordination number. What is coordination number? Coordination number is like this here. So this is called your coordination number, that is number of ligands it is attached to. Okay, so metal atom attached to how many ligands? So that is called your coordination number. So coordination number here it is 4. So for anything undergoing your geometrical isomerism, the coordination number should be at least 4, or you can say more than 4, that is your square planar complexes and your octahedral complexes. Only they will go and form your geometrical isomerism. Remember this, geometrical isomerism in your coordination compounds, only square planar complexes and octahedral complexes, they only will give you geometrical isomerism. Cis and trans in square planar complexes. So we will start with geometrical isomerism are two types, that is your cis and the other one is your trans. We know this from organic chemistry also. So similarly here also we are having the same thing. So now we will do of various complexes of different possibilities which are going to give your geometrical isomerism. So the first one is your cis and trans in square planar complexes. Square planar complexes. We will understand by examples, then I will give you the definition. So cis and trans isomerism, these are of type here M A2 E2. I'm showing with different colors, okay, so that you can understand. This is here, it is your 4 coordination number is 4, and here this is one ligand 1, and this is your second ligand 2. Okay, and this one is your metal complex. Okay, so this one is metal. So these type of complex where there is two ligand of different types. So what are the examples? The of platinum NH3 whole 2 Cl2. See here. If I take the example of this, is it not ammonia? It is 2, and chlorine it is 2. So there are two different ligands attached to it. So let us draw this. We can draw this in this form. So this is ammonia. Here it is ammonia. Here is chlorine. Here it is chlorine. So if we draw these kind of square complexes, what we say? This is your cis isomer. Another we will do where, see here, they are in transposition. These ligands are in transposition with itself. Okay, ammonia and H3. Now see, this is your trans isomer. Now we will do of molecule which has a metal like this, A2. These kind of these kind of metal type ligand type, they do not form your isomerism. Why they do not form? Because if you draw the spatial arrangements, or if you just rotate them around around an x-axis or y-axis, then you are going to get the same kind of molecule. So there is no change in the spatial arrangement, so they do not form your you can say your geometrical isomerism. Okay, so the next one is of the ligand is your M A2BC type. O nitrogen group if it is this side. Okay, NH3, NH3, Cl. Okay, so what is the type? This is cis because two ammonia group are on the same side. So this is cis. Now see here, if I do a Cl out here, again if I put your NO2 out here, ammonia in this side, ammonia in this side, is it not all this is trans to itself? So this is trans. Now when the ligand or the metal atom is of type MAB, your C and your D, where four, these are all square planar complexes we are discussing. So here four complex pyridine, you have ammonia, you have bromine, you have chlorine. So there are four different ligands. So what will they form? See here, chlorine. So if chlorine comes out here, this side, and bromine will go out here. Then ammonia this side, Py this side. This also can be. This is also one arrangement. The another possibilities is that this side, okay, where there was bromine. Now here there is NH3 ammonia here, and there is chlorine. So these are four. They are changing their position in different kinds of isomerism, giving different kinds of where chelates are not identical. Chelates are not identical. Chelates mean those which has two donor sides and they, they form a chelate kind of compound, a ring kind of compound with this coordination complexes. Okay, chelates. We have this glycine molecule and platinum complex. Okay, so what is glycine? Glycine is your NH2, CH2, COOH. So this is your glycine. Okay, so now see what are the complexes it can form. What are the possibilities? See here, platinum. Here NH2 is a donor atom, carbon is a donor atom, oxygen is also another donor atom. So they will arrange itself in the in the form of a chelates. They will form coordination compounds, okay, in the form of a chelates in a ring. They will form a ring kind of structures. See, this is NH, NH2, CH2, okay, COO, like this. So this is your cis one, cis. This is cis, and what is the trans will be? Trans will be like this: platinum, O, O, C, CH2, NH2, O, CO, NH2, CH2. Okay, so okay, see here, this ligand, the glycine with platinum, it forms a complex and a ring kind of structures, giving it's a chelate formation. So this is your trans. Here, see CO group in the same side. Here, CO group in the opposite direction. So it is trans. Now see, hold twice. So here platinum is there. There's two chlorine. Again, there's platinum, chlorine, PET3. So see, number it is two now, whole twice. So they are, they are adjusting itself to form these kind of bridge-like structures. So this is your cis one. See here, chlorine, chlorine, same PET in the same direction, and the other one is your trans. See, see, change this position. PET, you draw this side. Okay, here PET3, you draw this side chlorine, you draw this side chlorine, you draw. So this is your trans. So all possible square complexes, geometrical isomerism in square complexes we have done. Now we will go for geometrical isomerism in your square octahedral complexes. This is your MA4B2 type. Okay, which means here A is one ligand and the B is your another ligand. B2 is another ligand. So six ligand makes your octahedral complex. We know this. So now here, what if we take the example of okay? So if you take the center, since square planar complexes, so we have ligands on both sides, and there is ligands this side. So if it is like this, see, it is ammonia, NH3, okay, NH3, and your NH3 on all the sides, okay. Then other sides there is Cl and Cn. So see here, in all these four sides you have NH3 ammonia only. So this is cis type, okay. So again, if you draw, okay, so what will be the trans of this molecule? See here. See here, here the chlorine will be on the vertical lines and ammonia on all these sides, gives it this is your trans one. Okay, so this is the trans isomer, the trans geometrical isomer for this type of molecule. The second type, there are six ligands together. So one is A and another one is B. So if we take the complexes, this complex is also they form. So if we draw, we will have to draw the cis and the trans of this one. How will you draw? Again, see, draw the square planar complexes. Octahedral complexes is this way. Okay. Now, so if you want to draw the cis one, okay, there are three ammonia molecule. Okay, three ammonia molecule. Only one side ammonia, another side chlorine. So this is your cis one. Okay, and what will be the trans? You draw this octahedral complex of six ligands. So in trans one, what happens? One ammonia molecule will be on the other side. Okay, so this is your trans one. Okay, now another, the last one we have is MAA2B2 type. These type of molecules, they form complexes only when this AA means it has the same ligand. There is formation, or you can say chelate formation also. So this one, if you take the example, this type of complexes also shows cis and transisomerism. AA can be symmetrical or bidentate. This AA is your symmetrical or bidentate ethylene diamine. Suppose if we take the example like EN, okay, ethylene diamine. Okay, and B can be any other ligand. A will be your ethylene diamine. B will be any ligand like chlorine, then cyanide, then you have nitro, etc. It can be. Okay, so if we take the example of this platinum, En whole twice Cl2. Okay, so this complex. So how will you draw? See here, metal complexes here will be the platinum. Octahedral. So same way, you just draw this. Now, this side it will be En. This way it will be En, and this side your chlorine and chlorine. So this is yours, cis one. And what we will draw for the trans one? See here, it will be platinum. Hmm? Same way, you just draw for the rough sketch for your platinum. So what will it be? This side it will be En ligand. If you put En ligand here, chlorine, chlorine. So it is trans. Okay. Now we will go for optical isomerism compounds. So what will be the molecule which gives your optical isomers? Optical isomers actually, these are your enantiomers, which are mirror images of each other, can give optical isomers. So further, it has been found that these mirror images compound are non-superimposable on each other, and they do not possess any plane of symmetry. So optical isomers are those which are mirror images of each other, but they are not superimposable mirror images. These are called your enantiomers or your optical isomers. So the first example we will take MAA2 X2 type. So if this kind of molecule if you find, okay, so the example is like, take this example. If we are taking this example, so what we can do, this is octahedral complex. Okay, so this way it will be. Okay, so now see, if we draw like this, En. Okay, En for this is for chlorine, this is chlorine. One, what we can draw, a mirror image of this one. Okay, if we do Cl this side, okay, En this side. So is it not that this is a mirror images of each other? So this is, you can say, these are your optical isomers, which are mirror images of each other also. Okay, this is your cis. So these are two cis kind. So you can say this is your enantiomers. Enantiomers are those molecules which are identical in structures. These are mirror images but non-superimposable. Superimposable means if you put this molecule above this, you are not going to get the same one. It will not superimpose. Okay, so what will be the trans one for this? The trans one we have done for platinum complex. It is the same here also. Okay, so this is optically inactive, but this one is molecule is here, optically active molecule. So you have to remember which kind of type of molecules are there. So that time you can easily find what will be the enantiomers if you know the ligand type. So second ligand type we will do for optical isomers is examples of MAAB2 X2. Okay, so one ethylene molecule is there or bidentate ligand. The other one is another ligand. This is another ligand. So we have example of this. See this. Now see this example. Hmm. So what we can do again, if it is your octahedral complex, draw this way. Okay, there is a plane. Now decide where to put the ligands. Okay, so what we can do, NH3, suppose this is NH3. Here if you find this is to be En, chlorine, this is chlorine. So if you draw the mirror images of this, okay, NH3 Cl. So this is your En. See here, this is also showing mirror images, non-superimposable mirror images. So these are optically active. Optical isomer, optically active. Okay, this type also we have done. EDTA. Okay, minus EDTA. This is your hexadentate ligand complexes. This is your hexadentate molecule like this. It will be tetrahedral or square planar complexes. Square planar complexes only gives you geometrical isomers, whereas tetrahedral complexes never gives you a geometrical isomerism. Okay, so suppose this is N, this is C double bond O CH2 NH2, one molecule, N CH2 CH2 NH2, again CH2 NH2, this is CH2 C1O O. Okay, of complex. See, so this is your hexadentate complex. They feel chelating ligand. So if you put a mirror here, then also again you can draw another molecule. So this is optically active. CH2 CH2 and again CH2 CH2 C1O. This is of each other, and they are non-superimposable, and hence they are enantiomers, optically active. Okay, and M, A, B, C, D, E, and F, where all the molecules are different. Okay, so we have examples like this: platinum, BrO2, and I. See this? All molecules are your different. Okay. This is I, and here you have H3N, ammonia. Optical isomerism, like optical activity is shown by chelating tetrahedral and square planar complexes, but only very rarely it shows. In tetrahedral complex, only type which occurs in bis number 2, it is called bis chelates zinc 2 and copper 2 complex. In these complexes only you can see optical activity is there. Bis chelates. Okay, so what is the type is your bis chelates are like this. See, there is a there is a metal atom, this A, this B. Okay, they are linked like this, A and B. So they are connected this way. B, A, this is M, B, A. See, they are mirror images and non-superimposable, so they show optical activity. Bis, I will give you an example of bis salicyl aldehyde, boron 3 cation. See this. This is coordinated with this oxygen is giving ligands to boron. This is connected again. This oxygen is given. So this is the bis structure. See, these two are connected in this fashion. Okay. This is done of your geometrical isomerism in your coordination compounds. Basically, question comes from this topic and these examples which I have taken.